The objective for the question in this video is generating a confidence interval using the empirical rule. And this is my first video on this from your Newton Alta homework. All right. So again, if you haven't seen this objective before, you'd like to see more about it, click on more instruction, watch the videos, read through the text that they have, and then work on the questions after that. And again, I'm hoping that you've read at least the Chapter 8 introduction in your OpenStax statistics book and practice problems there, and then come back here and try working on this stuff. And again, the more instruction also very helpful. Alright, so I'm just going to go through it and let me show you how to work on a question like this. So this is generate a confidence interval using the empirical rule. Now hopefully you recall the empirical rule. That was that 68, 95, 99.7 rule related to normally distributed random variables, right? Bell-shaped, symmetrical bell-shaped curves. And I'll refresh your memory when we go through the question, of course. Alright, so in a questionnaire, a random sample of students were asked whether they studied for more than 4 hours to prepare for an upcoming chapter test. The questionnaire resulted in a sample proportion, right, so this is proportions, of p hat equals 0.58 with a sampling standard deviation, right, the sigma sub p hat, right, the standard deviations of the p hats. So the standard deviation of all the sample proportions for samples of whatever size they took. Remember the sampling distributions for proportions, that was covered in a previous video, I'm sure. So sigma p hat of 0.11. Who studied for more than 4 hours, right? So what happened here is they took a sample, right, these people that took this questionnaire, and of the people in that sample, 58% of those people study for more than 4 hours with a standard deviation of 11%, right, 0.11. Now, we're asked to use the empirical rule, write a 99.7% confidence interval for the true proportion of students who study for more than 4 hours. So when they say true proportion, they mean P, right? They mean the proportion of the population that study for more than 4 hours, not just this sample. Okay. So this is going to involve, the central limit theorem is coming into play here. All right. So again, I'm going back. I'll show you on a piece of paper. So hopefully you recall the central limit theorem for proportions, right? Because we're talking about proportions soon. This is CLT, central limit theorem. All right, and that stated that the distribution of sample proportions, right, when you had a population. So remember, P represented the population proportion, right? What proportion of the whole population, all students, studied for more than 4 hours. And this is unknown. Right? This is unknown. We're trying to guess what this is with a confidence interval. Right? That's what a confidence interval is. It's a range of guesses as to what some population parameter is. Now, we pull a sample of a certain size, right? Usually a large enough size to where this will apply, 30 or greater typically. And the distribution of all the sample proportions for samples of that size, remember, was normally distributed. With a mean called, mu sub p hat, and a standard deviation called, sigma sub p hat, where the mean, right, the mean of these p hats, the mean of this distribution of the proportions, the sample proportions, was equal to p. Again, but we don't know this. Right, we don't know p. And the standard deviation of the p hats was the square root of p times 1 minus p divided by, the size of the samples that were being taken, divided by n. But again, this is also unknown because I don't know p. So we guess, make a guess at p and create these confidence intervals. Right, now the initial guess, and I think I've mentioned this before. Remember, the initial guess, called our point estimate, it's a single value, a single point. The initial guess as to what p is our sample proportion p hat. Now they told us in this particular problem that that was 0.58. Right, so we're going to say that this is this mean of the p hats here, this p. We're going to have our initial guess be 0.58. And then using this guess, this point estimate, the standard deviation of the p hats would be the square root of 0.58 times 0.42, divided by, now we weren't told the sample sizes here, n. We could figure it out though, because they did tell us that this sigma p hat, the standard deviation of the distribution of the proportions, the sample proportions, was 0.11. Right, they did tell us this. So we're going to use this and this to help us create a confidence interval. So remember, we need an initial guess, we need a point estimate, and we need a margin of error. Right, the give or take. I'm gonna guess that p is 0.58, plus or minus some value, some margin of error, which was usually just it could be ME or MOE or EMB for error, EBM for error bound of the margin. We need a margin of error based on our confidence level. All right, now a confidence level is like a probability. It's a percentage, and the confidence level they gave us here was 99.7%. Right? For this particular question, they said they want us to write a 99.7% confidence interval. So this, again, the confidence level is 99.7%. This is the percentage confidence. I'm 99.7% confident that the true value of p will be in this confidence interval that we create. All right, so remember how our confidence interval is set up. A confidence interval. We're gonna guess that the true value of p is between two values, an upper bound and a lower bound, and the upper bound is formed by the point estimate, so our 0.58 point estimate plus the margin of error, and the lower bound of our confidence interval is the point estimate minus the margin of error. Right. Now we have to now they asked us to use the empirical rule to help us here. So I'm going to draw a little picture. So remember back up here, we said that the distribution of the p-hats that we're looking at here, these sample proportions, is normal with a mean of, we're guessing 0.58 and a standard deviation of 0.11. So I'll make a little number line here. Here's all possible different values of the sample proportions for whatever size samples were taken. We don't know that. This is normally distributed, so some symmetrical bell-shaped curve. Right, going to the left forever, right forever. Under the peak is our point estimate. Right, our guess at the mean here of 0.58. And then the standard deviation for these p-hats is 0.11. If you recall from earlier talks, earlier videos, that these inflection points, again, that should be on the curve. The same distance to the right and to the left here. This is a bad drawing, but these inflection points should be one standard deviation away. So if this is 0.58 and the standard deviation of the p-hats is 0.11, this value on the number line under this inflection point would be 0.69. This value would be 0.47. And that's one standard deviation above and below the mean. And we can go more, right? And here, doing here's 2 standard deviations and 3 standard deviations. Just keep going a distance of 0.11, 0.11. So this is 0.80, 0.91, right, for the 3 standard deviations above. 1 here is, say two standard deviations below. So 1, 2. Just subtract 0.11, so this is 0.36, and then 3 standard deviations below would be at 0.25. Right. And if you recall the empirical rule, remember the empirical rule stated the following: that within 1 standard deviation of the middle, right, within 1 standard deviation of the mean, so between 0.47 and 0.69, was approximately 68% of the entire area. Right? If I took the area under the curve between 0.47 and 0.69, that area would be about 0.68, right, about 68%. Within 2 standard deviations, right, so from 0.36 to 0.80, was approximately 95%. Right? So if I was asked to create a 95% confidence interval estimate of P, I'd be between these two values. But we were asked for a 99.7% confidence interval. And if you recall from that empirical rule, that was the area under the curve, right, or approximately the area under the curve within 3 standard deviations of the mean. Right, so from 0.25 to 0.91 here, under that part of the curve, you have approximately 99.7% of the entire area, and this is the number that was mentioned in our particular question. So if I'm trying to create a 99.7% confidence interval estimate of P, confidence interval for the population proportion, it would be this. The lower bound here is, again, you take your middle, your point estimate, 0.58, and I'm just subtracting 3 standard deviations. So it's 0.58 minus 3 times 0.11, right, which we already showed here was 0.25 for the so that's the lower bound. And then the upper bound of this confidence interval estimate would be, again, from the middle, 0.58, our point estimate, and then plus 3 standard deviations, right? So plus 3 times 0.11, and we already showed that that was 0.91. So 0.25 at the lower bound, 0.91 at the upper bound. There it is. All right. So, and then what all this means is that, based on my sample, right, based on our sample proportion 0.58 there, and whatever sample size was taken, based on that sample, I'd be 99.7% confident that the population proportion, right, that P is somewhere between 0.25 and 0.91, which is a pretty large range. I mean, again, the larger confidence level you have, the larger this interval will get. Because if you expand the interval, you cover a wider range of values. You'd probably be more confident that you have the actual value of P in there. And the smaller confidence level, right, the smaller percentage confidence you have, the smaller the confidence interval gets, right? If they asked for a 68% confidence interval, well, that would be from 0.47 to 0.69, right? If they asked for a 95% confidence interval for P, that'd be from 0.36 to 0.80. But here I'm saying that, I'm 99.7% confident that the true value of P, the population proportion, is from, somewhere between 0.25 and 0.91. That's all we're saying here. We don't know what P is, but I'm pretty sure it's somewhere in here. All right. So back here, that's what I'm entering. Here, lower bound we said was 0.58 minus 3 standard deviations, so 0.25. And then the upper bound was 0.58, our point estimate, plus 3 standard deviations. All right, so that 3 standard deviations would have been the margin of error. I probably should have written that out as well, right? So the margin of error, right, I'll just write it here. So we're seeing here that the margin of error is 0.33, right? 3 times 0.11. So there's your point estimate minus the margin of error, point estimate plus the margin of error. Okay, just pointing that out in case they ever ask for what was the margin of error. And then the upper bound, right, that was 0.91. And let's submit it and check it out. Wonderful. And they go through the whole rigmarole here. Now they mention z-scores. Now, again, the reason they mention z-scores is, because this was a normally distributed random variable, right? The z-score was 3 for these two values, right? Notice the 3, right? There were 3 standard deviations above the middle, 3 standard deviations below the middle, z-score of 3. And remember, z-score was just how many standard deviations away from the mean are you away from the middle. Okay. All right, so that's it for this first question, and more to come. Thank you very much for watching.